Has you ever peered into, the intricate machinery of a deep neural network and wondered what's really happening when it learns to classify data? Often feels like a magic black box, doesn't it? Well, today we're pulling back the curtain, diving into a fascinating new perspective that uses tools from an unexpected and truly elegant corner of mathematics, differential geometry. Welcome back to the deep dive. We take complex sources, find the important nuggets, and basically give you a shortcut to being well-informed. Our mission today: to unravel the intricate mechanics of deep learning through the lens of a groundbreaking concept known as Ricci flow. Now, this deep dive is brought to you today in partnership with Generative AI Futures. That's a new podcast by Byte Goose AI, and it's dedicated to exploring the real cutting edge of artificial intelligence. So if you're curious like us about the low-level details, the implementation, maybe the very principles guiding AI's next big steps, you'll definitely want to check them out. And today's discussion is actually a perfect example of the kind of deep technical exploration you can expect from them. We're specifically breaking down the paper Deep Learning as Ricci Flow by Anthony Baptiste and his colleagues. Our goal is to connect the dots, you see, between how deep neural networks transform data and this powerful mathematical concept, one that even helped prove the Poincare conjecture. Get ready for some genuine aha moments as we explore the hidden geometry of AI. Okay, so let's unpack this. We all know deep neural networks are incredibly powerful. I mean, recognizing handwritten digits, complex medical diagnostics.
Right, they do amazing things.
But, as the paper itself notes, our theoretical understanding of precisely how DNNs achieve such remarkable results lags behind their practical application. We use them all the time, but why they work so well, that's still a bit murky.
And what's fascinating here, really fascinating, is that despite all that complexity, DNNs seem to perform a series of geometric and topological simplifications as data passes through the layers. Imagine like a tangled mess of colorful strings, right? Each string is a data point, maybe it's class. Each layer of the DNN is working to untangle those strings, separate them into neat, distinct bundles, makes it easier to sort them out later. This process, they call it compositional representation, is how they efficiently approximate these really complex nonlinear functions.
So it's not just about, crunching numbers. It sounds like it's fundamentally reshaping the data's geometry in a very deliberate way. When you say simplifications, what does that actually look like? How does a network untangle those strings?
Well, when a DNN is trained for classification, its main goal is to take data points from these messy, complex, non-linearly separable classes and transform them into structures that are linearly separable at the very end, at the output layer. Think of it like this. Initially, your data points might be all scattered and interwoven in this high-dimensional space, hard to tell apart. But studies using computational topology have shown that as data moves through a well-trained network, it gets mapped layer by layer, until eventually points from different classes end up in distinct hyperspheres, almost like each class settles into its own perfectly separated, high-dimensional bubble.
Ah, okay. Like little distinct bubbles.
Exactly. Makes it crystal clear for the classifier to draw lines between them. This disentanglement is absolutely key to their accuracy.
That geometric transformation, taking tangled data and separating it into these bubbles, it sounds incredibly deliberate, almost intelligent. Does this suggest there's some deeper underlying principle guiding how these DNNs operate?
That's where the authors of this paper really dig in. And yes, it absolutely suggests a deeper principle. They propose a manifold hypothesis, which has three parts. First, real-world data points, images, text, audio, whatever, they often don't just fill up a high-dimensional space randomly. Instead, they tend to lie on a lower dimensional subset of that space, maybe disconnected. We call that a manifold.
Right, like a sheet of paper crumpled in a room. The room's 3D, the paper's 2D.
Exactly. Second, the DNN's real challenge isn't just memorizing points, but disentangling the important topological properties of this manifold, the fundamental connections and separations in the data, disentangling that from its messy geometry. And third, the DNN solves this by dynamically evolving the manifold. It effectively unravels the geometry, layer by layer, to reveal those core relevant topological properties.
So the DNN is essentially performing a kind of sophisticated geometric flow on the data itself.
Precisely.
Okay, so this brings us to the key question. Where does Ricci flow, this concept from pure mathematics, fit into this picture?
Right. If we connect this to the bigger picture, Ricci flow is a really profound tool in differential geometry. It's a process where a manifold, a geometric space, evolved over time by smoothing out its curvature. Imagine a bumpy, irregular surface. Ricci flow will gradually smooth out those bumps, making the surface flatter, more uniform. But crucially, it preserves the fundamental shape.
Okay, like ironing out the wrinkles but keeping the overall form.
Exactly. This process was famously central to, well, Grisha Perelman's proof of the Poincare conjecture, a huge problem in math. Intuitively, Ricci flow helps simplify a complex shape so we can understand its fundamental topology. And the parallel here is how a DNN seems to simplify and untangle data, kind of mirroring this geometric smoothing. It's quite appealing.
It's amazing how often answers in one field pop up from discoveries in another. And speaking of connections, before we dive deeper into the paper's specifics, it's worth noting this whole idea of data living on a manifold isn't brand new, right? Geometry and topology in forming complex systems has a history.
Oh, not at all. While using Ricci flow is relatively recent, the concept of manifold learning itself goes back decades. You had researchers like Tenenbaum, De Silva, Langford with IsoMap, or Saul and Roways with LLE. This was back in the early 2000s. They were already exploring algorithms to find that underlying low-dimensional manifold structure hidden in high-dimensional data, trying to preserve the intrinsic geometry.
So trying to flatten out that crumbled paper without tearing it, essentially.
Kind of, yeah. And even earlier, just the idea of feature spaces in machine learning implicitly suggested data points might cluster or form regions you could separate geometrically. So this paper, it's building on a rich tradition of viewing data geometrically, but it's using this remarkably powerful new mathematical tool, Ricci flow, to do it.
Okay, that context is helpful. But back to the flow itself. That analogy is powerful. But Ricci flow is continuous, right? Smooth evolution over time.
Yeah.
Deep learning, though, it happens in discrete steps, layer by layer. With discrete data points, how do you bridge that gap? That seems like a big hurdle.
You've hit on exactly the challenge the paper tackles. Continuous Ricci flow works on smooth manifolds, evolving this thing called a Riemannian metric. Think of it like the ruler for distances and curves on a continuous surface. But deep learning's flow is discrete, both in time-distinct layers, not a continuous stream in space it operates on a finite set of data points, not a smooth manifold. So the authors had to adapt. They used discrete analogs of Ricci curvature, specifically something called Foreman-Ricci curvature.
Foreman-Ricci.
Yeah.
Right.
And it has this really nice combinatorial construction. That means you can compute it directly on a graph, which is perfect for representing discrete data points and their connections. And importantly, it's efficient to compute, practical for large data sets.
And here's where it gets really interesting for me. This isn't just some abstract theory. These discrete versions of Ricci flow, they actually have practical uses outside deep learning that kind of pave the way, right?
Absolutely. Discrete Ricci flow has turned out to be surprisingly versatile. For instance, it's been used pretty effectively for community detection in networks.
Which sounds a lot like classification. Finding groups.
Exactly. It's very related. It's also been applied to things like rewiring graph neural networks to optimize their structure, avoid bottlenecks. It can stretch out regions of negative curvature, basically evolving the network's geometry to improve how information flows. So this prior work showed that discrete Ricci flow isn't just a mathematical curiosity. It's a real tool for understanding and manipulating network structures. That made it a compelling candidate for looking at neural networks.
Okay, so we have this elegant theory. Discrete Ricci flow has some track record. The next critical step is, how do we actually measure this Ricci flow-like behavior inside a working deep neural network? How do you quantify that untangling process?
Right. The authors developed this clever computational framework. First, they treat the output of each hidden layer in a trained network as a kind of snapshot of the data's geometry at that specific stage. Then, for these data points, they construct a graph. A k-nearest neighbor graph. Each data point is connected to its k-closest neighbors. This graph sort of approximates the local distances and relationships right there at that layer.
Okay, building a local map at each step.
Exactly. Then they calculate the Foreman-Ricci curvature on the edges of that graph. This curvature basically measures the local connectivity. Maybe think of it as the curvedness of the data representation at that layer.
Curvedness in a graph. How does that work?
Well, intuitively, think about how easily you can find alternative paths between nodes, or how sparse or dense the connections are locally. High positive curvature might mean a tight cluster, lots of redundancy. Negative curvature suggests things are spreading out, separating. And by analogy with the continuous Ricci flow equation, they propose that the change in total distance between data points from one layer to the next should be roughly proportional to the total curvature of the data at the current layer.
So high curvature predicts a certain kind of distance change as you go deeper.
That's the idea. If it's highly curved, you expect a certain change as it flows to the next layer.
And this measurement, this relationship between distance change and curvature, this leads to what they call the Ricci coefficient.
Precisely. The Ricci coefficient, they use the Greek letter rho, troll AI. It's a Pearson correlation coefficient. It quantifies how strongly the expansion or contraction of distances between layers correlates with the total curvature at a given layer. Now, here's the crucial part. A negative Ricci coefficient indicates the presence of what they call global Ricci network flow-like dynamics in the DNN.
Negative means it's happening.
Yes. A negative value means that as the curvature decreases, as the data gets smoother or less bunched up, the distances between points tend to increase. They separate. And conversely, as curvature increases, distances tend to decrease. They converge. It's this specific inverse relationship, this kind of geometric push and pull, that signals the network is effectively doing that untangling we talked about.
Okay, that's a very specific, measurable signature. It sounds incredibly detailed. So with this new metric, what did their experiments actually show? How do real networks behave?
Well, their experimental setup was pretty extensive. They trained over 1,500 DNN classifiers, different widths, different depths, a real variety of architectures, and they tested them on a range of data. They have 3 synthetic data sets, cleverly designed with different levels of entanglement, sort of easy, medium, hard untangling tasks.
Okay, controlled test.
Right. And then real-world data sets like MNIST, distinguishing digits like 1 from 7 or 6 from 8, and fashion MNIST, classifying things like sandals versus ankle boots. This breadth was important for generalizing.
Makes sense. So what did they find when they applied this Ricci coefficient across all those networks and data sets? Did this Ricci flow-like behavior actually link up with performance?
Yes, and this was the really significant takeaway, a genuine aha moment, I think. They discovered that a stronger global Ricci network flow-like behavior, which means that a more negative Ricci coefficient, correlates with higher classification accuracy for well-trained DNNs.
Wow, okay. A direct correlation.
Yes. And importantly, this correlation held up regardless of the network's depth, its width, or even the specific dataset being used. It really suggests that this geometric untangling isn't just some accidental byproduct. It seems to be a fundamental mechanism tied to effective learning.
That is a big deal. A generalizable metric like that is incredibly valuable, especially in AI, where things can feel like guesswork sometimes. Did they find any other interesting patterns, maybe related to different data types?
They did. They noticed that the optimal K, remember, that's the number of neighbors used to build the graph. At each layer, it seemed to vary depending on the task and the data. For the synthetic data, a low K often worked best. This suggests that for simpler, maybe already somewhat separated data, the DNNs focused more on separating points from different classes, pushing them further apart.
Good at widening the gaps.
Right. But for the more complex real-world data like MNIST and fashion MNIST, a higher K was often optimal. This hinted that maybe here, the DNNs were more focused on converging points within the same class, making the clusters for each category tighter and more refined.
So different strategies, sometimes separate, sometimes converge.
Exactly. It reveals that DNNs might employ different geometric strategies depending on the nature of the data they're dealing with, optimizing for separation or convergence as needed. It's quite nuanced.
So wrapping this up a bit,
Yeah.
what does this all mean for us? For people designing AI, deploying it, just trying to understand it better? This isn't just theory, right? It has real implications.
Definitely. If we connect this to the bigger picture, this research really motivates using these tools from geometry differential and discrete geometry to improve explainability and deep learning. Think of the Ricci coefficient as maybe a kind of geometric health check for your network.
Health check, I like that.
It could become a really valuable tool for model selection. If a network shows strong Ricci flow-like behavior, a consistently negative strong coefficient, it suggests its internal data transformation is working effectively. It's likely to generalize well, not just memorize noise or overfit. This could help us design and pick architectures that are fundamentally better suited to the job.
That's a powerful idea. A quantifiable measure that might predict generalization. Could this geometric view lead to more robust systems, maybe more efficient ones?
Absolutely. And while this paper focused on the global flow across the whole dataset, future work could look at local Ricci flow dynamics. Imagine being able to pinpoint which specific data points or which regions of the data manifold are showing strong local flow behavior.
So zooming in on specific parts of the data.
Exactly. This could give us a whole new way to approach point-specific uncertainty quantification. Understanding why a network is more confident about classifying this point versus that point. It could also help detect anomalies or out-of-distribution data. If a new data point isn't flowing correctly through the network's learned geometric landscape, maybe it's an outlier.
That makes sense. If it doesn't fit the flow, it doesn't belong.
Right. This whole geometric perspective really opens up a new frontier for diagnosing and improving AI models at a much more granular level.
What an incredible deep dive. Seriously, we've gone from the mysterious insides of neural networks all the way to the elegant math of Ricci flow. And we've discovered this new lens, this geometric lens, to understand and maybe even optimize these powerful AI systems. The idea that deep learning might basically be geometrically untangling data, smoothing out its complexities to find the core structure, that's really profound.
It is. And this research, by proposing a clear, computable metric for this Ricci flow-like behavior, it really underscores how fundamental math concepts, even from pure geometry, can light the way forward in cutting-edge AI. It suggests there's just so much more to uncover if we look at these problems through that geometric lens, moving beyond just, the standard linear algebra and calculus toolkit.
So for you, our listener, maybe consider this. How else might seemingly unrelated fields of mathematics hold the keys to unlocking AI's deepest mysteries? It's a powerful reminder, I think, that the most surprising insights often come from connecting dots across different domains. Geometry, topology, maybe something else entirely waiting to be applied. We really hope you enjoyed this deep dive into the geometry of deep learning. And if you are fascinated by these technical details, the math, the future of AI implementation, its core principles, definitely check out that new podcast, Generative AI Futures, brought to you by Byte Goose AI. You'll find more explorations just like this one, diving deep into the how and why of AI. Thanks for joining us on the Deep Dive.